If clocks stopped agreeing, schedules unraveled, and timestamps lost meaning, how would the world actually run? This is not time freezing. This is civil timekeeping failing. The systems that synchronize our lives going out of alignment. Today, we test what happens when time, as an infrastructure, stops working. Modern society runs on Coordinated Universal Time, UTC, stabilized by atomic clocks across national metrology labs. GPS satellites distribute precise time derived from onboard atomic standards, allowing receivers to synchronize down to nanoseconds. Networks use NTP and PTP to cascade time from stratum 0 sources to servers, exchanges, grids, and phones. Finance enforces sub-millisecond timestamping for orders and trades to ensure fair sequencing and auditability. Power grids timestamp phasor measurements for state estimation. Losing phase-aligned time corrupts situational awareness. Factories, telecom, aviation, rail signaling, and databases depend on time order to coordinate motion and data. At the human level, routine runs on synchronized clocks, transit schedules, payroll, medical dosing, and legal records. Imagine a global anomaly. Satellite time signals drift beyond tolerance, and ground labs cannot agree on UTC corrections. Top-level time servers disagree by milliseconds, then seconds. Downstream, networks propagate conflicting epochs. Cell towers relying on precise timing for handovers see drift. Calls drop as time slices misalign. Dispatch systems that merge GPS time with local station clocks generate contradictory train departure sequences. Airports revert to manual procedures when departure slots cannot be reconciled across systems. Delays multiply. Container ports record gate-in events later than gate-out due to reverse timestamps, flagging audits and holds. Distributed databases rely on monotonic ordering. When wall clocks regress or jump, conflict resolution degrades. Incident responders lose the ability to reconstruct sequences. Logs appear out of order, obscuring causality. Payment networks see authorization requests timestamped after settlement. Fraud systems trigger false positives. Phasor measurement units cannot align angle data without a common reference, degrading grid state estimation. Robotic cells and conveyors desynchronize. Supervisors impose manual interlocks to avoid collisions. Throughput drops. Hospitals pause automated medication scheduling and verify dosing against paper charts and analog wall clocks. Legal systems that depend on filing order and deadline times issue blanket extensions to prevent procedural errors. Journalists revert to eyewitness sequence logs and analog timecodes to cross-verify event order. Environmental monitoring relies on synchronized sampling to compare stations. Desync skews trends. Satellite imagery and ground truth misalign, complicating data assimilation for weather and climate models. Ocean buoys and floats timestamp temperature and salinity profiles. Drift undermines current reconstructions. Seismic networks need tight time to locate events via arrival time differences. Localization precision degrades. Agencies prioritize retime stamping pipelines with cross-correlation and manual QA, slowing releases. Exchanges suspend microsecond timestamp guarantees. Order sequencing falls back to deterministic engine order. Regulators permit relaxed accuracy thresholds and require audit trails using engine sequence IDs over clock time. Shippers face detention disputes as pickup and delivery proofs conflict. Contracts pivot to scan order rather than time. Retailers extend promotions. Payroll providers shift to sequence-based cutoffs, reducing disputes. Uncertainty raises costs, but systemic collapse is avoided by rule modifications and manual buffers. Telecom operators switch from GPS to holdover oscillators and EPRTC sources, rationing precision time to critical nodes. Cloud providers enforce monotonic time at the application layer. APIs reject backward jumps to protect ordering. Process control systems shift to local deterministic cycles. Cross-plant coordination loosens, but safety interlocks hold. Aircraft, ships, and rail revert to inertial and radio aids. GPS remains usable for position with caution on time. Organizations publish sequence-based procedures, first in scanning, chain of custody logs, and manual sign-offs. Schools standardize on analog wall clocks and radio beacons. Transit operates on station master time. Clinics verify dosing intervals by elapsed timers rather than wall time, reducing dependence on external sync. Media houses stamp footage with camera internal counters and slate sequence IDs to maintain order. Clear messaging frames the issue as a synchronization failure, not a metaphysical crisis, stabilizing sentiment. Standards bodies coordinate a provisional UTC without leap adjustments, prioritizing stability over absolute accuracy. ICAO and IMO issue NOTAMs and circulars, clarifying operational status of GNSS timing and required backups. Securities regulators align on relaxed timestamp policies and standardized sequence auditing across markets. Security teams harden against replay and out-of-window attacks, shifting to nonce and sequence-based validation. Disaster response and research communities share best practices for realigning datasets and field operations. Operators deploy multi-constellation timing using GPS, Galileo, Beidou, and GLONASS with cross-checks and anomaly detection. Network cores adopt enhanced holdover, oven-controlled oscillators, and chip-scale atomic clocks to bridge outages. Distributed systems pivot to logical time, Lamport clocks, vector clocks, and consensus logs for authoritative order. Trading venues publish sequence-indexed audit trails and cryptographic proofs, decoupling fairness from wall clock time. National labs rebuild ensemble time scales with improved steering and machine learning anomaly filters. Environmental datasets are reprocessed with cross-correlation, radiance matching, and station pair alignment. Grid operators integrate algorithms that use relative angle differences and local oscillations when absolute time is unreliable. Rail and air introduce sequence slots and ground truth token passing, with analog master clocks as human references. Curricula teach time as infrastructure, covering synchronization, holdover, and safe degradation strategies. Business continuity plans maintain hybrid analog-digital processes and on-site reference clocks. People accept small inefficiencies in scheduling in exchange for predictable, safe operations under uncertainty. The lesson is pragmatic. When clock time fails, systems fall back on order, locality, and verification. We do not need perfect clocks to function, but we need reliable ways to agree on before and after. Time in practice is an agreement held together by engineering, policy, and routine. When it fractures, resilience is about graceful degradation and clear rules. 3 pillars carry us through: local autonomy with safe defaults, networked consensus for ordering, and transparent human oversight. Practical steps include monotonic timing in software, sequence-based contracts, analog backups, and routine drills. We design for uncertainty by assuming the clock can lie, and by building systems that still tell the truth about order. When schedules bend, people adapt. Clarity, patience, and well-tested fallbacks maintain trust across institutions. In the scenario where time stops working, society does not end. It switches modes. With the right engineering and steady communication, we navigate, measure, and decide effectively, even when the second hand strays. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.